Hello, ladies and gentlemen. My name is Anton. I'm representative of the Belarusian team, and I want to introduce you our solution for the problem number 2, cutting the air. To get started, let me remind you the problem. When a piece of thread is wired around with a small mass attached to its frame, a distinct noise is emitted. Study the origin of this noise and the relevant parameters. So, accordingly, I introduce you our work plan. So, first of all, we are going to use a qualitative explanation of our phenomenon. Then we are going to proceed our experiment path, where we are going to make all our experiments. After that, we are going to try to build some theoretical model for this phenomenon, and finally, we are going to compare the results of this path and make our conclusions. So, first of all, let's start with qualitative explanation of the phenomenon. So, actually, we are having two interesting phenomena in our problem. First of all, this appearance of the sound itself, and secondly, as you might hear, appearance of characteristic pulsations. Now we are going to explain them. So, first of all, the appearance of the sound. There are two possible reasons for the sound. First of all, there is a conspicuous vortex shading from the surface of the thread, also called common vortex split, and secondly, there is the vibrations of the thread. So, and also let's try to explain the pulsations of our sound. So, first of all, the Doppler effect, also called Doppler shifting, and secondly, the rotation of the thread because of the movement on the thread itself. So, now let's proceed to our experiment. So, first of all, we are introducing you our experimental setup and its important part. So, here you can see the source of adjustable voltage, the drive electro engine, the attachment of the wire or the thread or thread itself, and the microphone or camera depending on the experiment. Also, we introduce you the rotating plane view and the side view to get you better understand the principle of work of our setup. So now let's also define the boundaries of the useful spectrum. Because we are having some sound here and also we have some noises, we need to define it. So to do this, we record the sound of pure noise without the useful sound. After that, we record the sound of our wire and then we compare it. Even visually, we can distinguish the borders of useful spectrum, and comparing them, we get it. So here it is. Now let's define the useful parameters of our sound. So first of all, the sound spectrum, also the volume of the sound, the characteristic frequency also is defined as a peak in the spectrum, the frequency or period of pulsations, the maximum frequency and minimum frequency. Now let's proceed to the experiment. So first of all, we've studied the dependence of characteristic frequency from the frequency of rotation of our thread using different materials of our thread. Here you can see the result. From metal and nylon thread. As you can see, the results are quite near to each other. That's why we can say that the material in this case does not important. So, but if to think a bit more, we can see that here is our spectrum, and here is the spectrum of some noise. For example, when we play on the guitar, so number of harmonics. We can't see such harmonics in our spectrum. That's why we can say that the material and the force vibrations of our thread are not important. Now let's study the noise itself. So here you can see the dependence of maximum frequency of our sound from the frequency of rotation. It has a linear approximation since it fits quite good. So also you can see that it goes from zero, and the slight coefficient beta can be neglected, and that's why we'll study the dependence of coefficient A from different parameters. So first of all, let's adjust the length of our thread. Here you can see the result. The result is also quite linear, and that's why we can conclude that the final maximum frequency somehow linearly depends on the frequency of rotation and the length of our thread. Now the same experiment was done about the diameter of our thread. Here you can see the result. So again, we will try to approximate it somehow. Here you can see the result of our experiment is the dependence of the slope of our graph from diameter. So first of all, the simplest decreasing function is hyperbolic. That's why I try to use it, and the result is quite good. And also we introduce the linearization for this graph. And finally, using our experience, we can conclude that the final maximum frequency can be counted using this formula. Now let's study the influence of the bob in our task, since we have it in our program. So there were two tests produced. First, we recorded the sound without the bob, and secondly, we recorded the sound with big mass. So it had the diameter about 5 or 10 centimeters. Here you can see the result. First of all, the volume of the sound is the same. Secondly, we can see that the same characteristic frequency. And finally, which is the most important, we have the same envelope. That means that the big bob do not affect the sound actually. The same test was produced again, but the big bob was replaced with a small one, so it has a diameter about half of a centimeter. Here you can see the result. Let's analyze it. First of all, the volume has changed. Secondly, the characteristic frequency also has shifted to its initial value. And finally, we can notice that the sound has absolutely different envelopes. That means, from these two experiments, we can actually conclude that the contribution of our bob to the spectrum depends only on the size and shape. Now let's conclude about the final cause of the sound in our problem, since we've put this task in the beginning. So, since the material of our thread is not important, we can conclude that the vibrations of the thread are definitely not important. That means that the consequent vortex shading is the real cause of the sound. Now let's proceed to the theoretical model. Here you can see some principal approximations of our model. First of all, the angular velocity of the thread is constant, and the influence of the gravity on the angular velocity can be neglected. The sound is explained by the consequent vortex shading from the thread surface, and also called common vortex strip. The frequency of vortex shading coincides with the frequency of the sound, and the vortices are created by the energy carried away by the vortex flow. Now let's start. First of all, we made some search for some previous researchers and found the person whose name is Vincent Stuchel, who studied the flow in gas. Particularly, he studied the vortex flow, some condition of flow between laminar and turbulent, and his results are that when we have the vortex flow, there is some number which connects the linear velocity of our object is dimensions and the frequency of vortex shading. Using the conditions for the thread of our theory, we can get the dependence of frequency in each piece of our thread from its coordinate. Now let me introduce the main values which we are studying in our theory. First of all, the frequency emitted by a small section of our thread, the spectral density or spectrum of the sound, and the integral intensity of the sound. So now we introduce our theory. So let's take a small part of our thread and write its area. So you notice that it's differentially small. Secondly, we take since we have some vortex flow, we can write the force of air resistance for this piece of the thread, and multiplying it by coefficient k and the velocity of this piece, we can take into account the losses such as heating, and we can get the sound power emitted by this section. And finally, taking into account the condition, the connection between the intensity and the power, we can get the intensity of this small piece of thread. Pay attention that this intensity depends on the distance to our listener. So here you can see the final results of our calculation. It seems quite great, but actually it's not very difficult. So the main part is that here you can see some big expressions connected with time, and here you can see some expression connected with frequency, since the spectrum is the function of frequency. And as we to connect these two things, we need to make the replacement of variable, and we are doing it, and the result is the functions of frequency. Now let's compare the result of theoretical model and the result of the experiment. First of all, the characteristic frequency, the frequency characteristics of our sound. So here you can see the maximum frequency, the minimum frequency, and the characteristic frequency. Special attention should be paid to characteristic frequency, since contrary to the expectation of huge some expressions and so on, we'll get the simple expression which contains the two independent variables and the constants which depends only on the position of the listener. Now let's also try to compare the spectrums of our sound, theoretical and actual. And finally, you can see the comparison of the amplitude mapping of our sounds. As you can see, the convergence is quite good in the volume of the sound as a whole and in the volume of a simple pulsation. So now let's make our conclusions and sum up our work. So first of all, let's form out the list of relevant parameters of our sound, since we are studying something and we need to answer the question what is important. So, first of all, let's divide them into several categories, like aerodynamic properties of our thread, properties of material, properties of rotation, and properties of gravity. So, first of all, we've proved that the material of our thread is not important. That's why we can cross out all the properties of material. The same we can do about the plane of rotations, which is not important too. And finally, we can name the relevant parameters. They are length and the diameter of the thread and the frequency of rotation. So, and first of all, and after that, let's sum up our work. So, what we've done? We've found the original of the sound, and also we've found the relevant parameters. This was the condition of the problem. But we've done actually something else. And this something else is building a theoretical model in which we've included the previous researches for this topic. We've invented a quantitative description of the phenomenon, and finally we've got all the properties of the sound. And that gives us that now we can predict the emitted sound. Now let's make conclusions. The sound comes as a result of vortex shading from the surface of the thread and common vortex stream. Typical pulsations occur as a result of both the Doppler effect and the changes in signal attenuation with distance. And the quantitative conclusions. The frequency characteristics of each piece of the thread, as well as the whole thread, are defined by the Tuchel equation. The characteristic of frequency is determined by the position of the listener, as well as the linear dimensions of the thread, parameters of the rotation. Shape of the spectrum is determined by the speed and the parameters of the thread, and the percent of the bob just as its own sound, which depends only on its size and shape. I guess that's all. Thanks for your attention.
So we have questions of the opponent.
Could you come back for slide 9?
Okay.
Yes. Don't you think that the position of the microphone in relation to the wire is relevant?
Okay, of course I agree with you. So actually we even made some studies to this topic, and I even can present you results if you want sometime. But we didn't. So we've adjusted the position of microphone too, and
okay, you talked about the Doppler effect, but you didn't analyze this in the experiment. So
okay, I understood your position. So actually, I can make you some demo for theoretical part. So first of all, we've proved that the main effect is changing of distance. So, but actually, I can show you some video. So this is the spectrum for the Doppler effect, and without it, here you can see the demo. It will work.
okay,
So as you can see, it doesn't differ much.
Okay, don't you think that the mass attached to the wire is important?
As we've proved, that first of all, the dependence, our sound depends only on size and shape of our mass. Because first of all, the mass influences only on our tension of our thread.
Okay.
And we proved that the force vibrations of the thread are not important. That's why the tension is also not important.
Okay.
We can ignore it. And also,
why is the tension important? I'm sorry, you said that it's not important.
As I said, yeah, it's not important because the main mechanism of oscillation of our problem is vortex flow. And as we said, the tension does not take any effect.
Okay, could you come back for slide 17, please?
Which one? Excuse me?
17.
17, okay. Yeah, this one?
Okay, how do you get this curvature of the graph? Yes. What is the difference between the two graphs?
I've said that actually there is particularly no difference, almost no difference, because that was my point, that the big bob, so the big mass, doesn't which has big linear dimensions, which does not affect the sound. And
Okay.
All right. We move on to preparation of the opponent then.